My name is David Paulson. I'm an assistant professor of mathematics at Virginia Tech, and welcome to part 3 of a series of videos where we explore Fourier series through the lens of linear algebra. In part 1, we reviewed inner products and their associated norms from linear algebra. In part 2, we looked at orthogonality using inner products. And now we've reached part 3, the highlight of the series, where we look at Fourier series as best approximations. Finally, in part 4, we will explore the convergence of Fourier series and introduce the main tool, which is called the Dirichlet kernel. But now, the highlight, Fourier series. Why Fourier series? Well, Fourier series give us a different view of the world around us that allow us to decompose objects around us in a different way. They're part of a field called Fourier analysis that has seen tremendous success with applications. For example, Fourier analysis has been used in image compression. For example, you would not be watching this video here if there were not for image compression. Other applications are that Fourier analysis unlocks the mysteries of the equations that describe the world around us. Differential equations, especially partial differential equations, describe many of the natural phenomena around us, anything from heat to waves to Schrödinger equation and quantum physics and whatnot. And Fourier analysis is often a key tool in the exploration of these equations and trying to understand their solutions. Finally, they are closer to home, the applications of Fourier analysis. You can find them in MRI scans, where you do not need to look inside a patient to understand what is going on, but rather you can take information around a patient and patch them together to understand what is inside. So those are some of the motivations of why we would care about Fourier series. Now, our goals today are not applied in nature. They are more along the lines that we want to be able to calculate Fourier series and recognize convergence properties. So with that, let's move on and do some math. In part 2, we talked about the concept of an orthonormal basis, or an orthonormal set. A set where we had vectors that were all pairwise orthogonal, each of which had magnitude 1. Here we have a list of sines and cosines, an infinite list, and I claim that this is an orthonormal set when these functions are correctly scaled. Now, the key observation behind that is just looking at integrals of cosines and sines, pairings. Now, here I wrote up integrals of cosine paired with cosine and sine with sine. You should also look at integrals where you pair cosines with sines, but these are the kind of integrals that you may have seen in calculus. And so perhaps you should pause the video now and see if you can recall how to perform these integrals from calculus. But if you believe that this is an orthonormal set of functions, then we could look at a subspace that is spanned by finitely many of those. And then the key result from the part 2 of our videos was that if you take a function and you project it onto the subspace, then you get a best approximation of that function. That is, if you want to approximate a function just using cosines and sines and a constant function, then you can do that by projection. And the projection tells you exactly how to compute the coefficients that appear in this linear combination. Now, for applications, it seems a little inconvenient having all of these 1 over square root pi's floating around. So what people have done is that they have sort of come up with a different way of writing things. That is, they've incorporated these constants 1 over root pi into the appropriate constants, a's or b type of constants. So a trigonometric series is just a series of cosines and sines, just as we had before. Now, if on top of that, your coefficients are chosen the way they should be according to projections and incorporating the constants that we had before, you obtain what is called a Fourier series. So now we have seen what a Fourier series is, and its motivation comes from taking a best approximation. That is, you're saying if you have a function f and you want to approximate it with sines and cosines, you do it through the projection. And instead of just taking a finite number of terms in your sum, you say, well, why not just take infinitely many? Because presumably your approximation gets better and better the more and more information that you take. But it leaves the question, clearly a finite approximation is likely not to give you exactly the function you started with. But what if you take infinitely many terms? We think that we get closer and closer, so do you actually recover the original function? Well, let's explore this. Let's start with a function f of x equals x on the interval 0 to 2 pi. And let's then just compute the Fourier coefficient. Now, computing the constant coefficient is just the integral of x, not so bad. But when you look at the higher order coefficients, you are taking an integral where you're pairing x with a cosine or a sine. You may have recalled seeing integrals like this in calculus, and the trick is to use integration by parts, where you differentiate away the x, and then hopefully end up with something you can compute. Now, in the specific case of the specific function that we're looking at, the coefficients in front of cosines become 0, and then we get a very concrete answer for the sine coefficients, so we can write out the Fourier series. Now, is that the function x? Does it recover the function x? That is unclear at the moment. It is not obvious that this big series gives you x at every point. But let's make a little observation. If you plug in x equals 0, then all the signs in the series disappear, and you're just left with a pi. Similarly, if you plug in 2 pi, all the signs disappear, and you're left with pi. So you evaluate to pi, whereas the function at 0 evaluates to 0, and at 2 pi it evaluates to 2 pi. This seems problematic. We did not recover the function f at the endpoints. But this is not so bad. The endpoints were specific, very special there. Now, there is a general theorem that is for the convergence of Fourier series that says that if a function is integrable with period 2 pi and piecewise differentiable, such that at any point where you're not properly differentiable, you can take a right limit and left limit of the function and its derivatives, then the function f converges to the average of what happens between the left approximation and the right one. Okay? So in the particular case of the Fourier series that we had in the previous example, then note we were looking at f of x equals x on the interval 0 to 2 pi. Now, the theorem talks about periodic functions, so you can extend that function. Okay? And then note, for example, at 2 pi, then coming from the left, your function is heading towards 2 pi, whereas if you come at it from the right, it's heading towards 0. The average is pi, which is exactly what we got on the previous slide. And so this is one thing that happens. But in between, where there are no jumps in your function, you recover exactly your function, which is great. Now, there are further theorems. One can loosen the conditions of this theorem, but this is sort of the highlight theorem for this section of the series of videos. And we'll talk a little bit in part 4 about how you would go about proving something like this. Now, are we stuck to the interval 0 to 2 pi? What about other intervals? Well, let's look at a different interval, 0 to L, where L is any number. You can still write a Fourier series there. Well, first of all, you can write a trigonometric series where you just scale your sines and cosines appropriately. That is, you look at functions that are now L periodic instead of 2 pi periodic from before. And if the coefficients are appropriately obtained, that is, again, you have to scale appropriately the cosines and sines and the coefficients out front, then you still get a Fourier series. And the previous theorem about convergence still holds true. And what is more is that you're not just stuck to an interval 0 to L, you can actually move it around, because as long as you have L periodic functions, you don't have to integrate from 0 to L. You could integrate from minus L over 2 to plus L over 2, or any kind of an interval of length L. Let's take an example. Let's, for example, look at the function f of x equals x again, but now in the interval minus pi to pi. You can calculate the coefficients as before, using integration by parts. You can see that the coefficients look different for the sines this time. The cosine coefficients are still 0. And you get a Fourier series here. And you can evaluate it, for example, at 0, where you can see you get 0, you actually recovered the right value of the function. Whereas if you plug in, say, minus pi or pi, the outcome's 0, okay? And which matches with the jumps that you have in the function. See, the function jumps between minus pi and pi, which average is 0, which is exactly what that Fourier series spits out. So with that, we've come to the end of this video. In part 3, our objective was to be able to calculate Fourier series of given functions and recognize convergent properties of Fourier series. The highlight was the convergent theorem that we had. That is, Fourier series for good functions, that is, functions that just have some jumps in them, actually converge to the function, so they're great. They're good approximations. And then we did a couple of calculations where we calculated Fourier series. Now, in part 4, we will look at some of the tools that are needed to understand the convergence theorem that we just stated. And that is coming up in the next video.